This application section can always be difficult. I picked 3 problems that hopefully represent a decent amount of the ideas. And if you have more questions, we can always add more to this, and I'm happy to do that. Just let me know any of these that you really want to see that you're having trouble with. So this is number 25. You've got you're standing 50 feet from this church, and you're trying to figure out how tall the steeple is by taking some angles of elevations. Where I would begin is we've got this 35-degree angle right here, and it's part of a right triangle. I mean, we're assuming, you have to assume a little bit, the ground's probably close to, where we could come up with a line that's level, and we assume the wall is probably plumb, so they should be meeting at 90 degrees. If that stuff's true, then I can figure out the height, at least of the building right here. I'll call it h sub b, since I've got a total height over here for h. So let's set that up. That would be tangent because I've got an opposite and an adjacent side. And I'm taking the tangent of 35 there. And that'll give me height of the building over 50. So 50 tangent 35 will be the height of the building. Now I am in degrees here, so make sure you do put your calculator in degree mode. When I did that, I got about 35 feet for the height. And I'm just going to round. I think this should be close enough. Now the next thing I've got here, I've got this really big triangle from the ground up to the top of the steeple there. So we'll set up a similar ratio. Tangent of 47 degrees. Now, it'd be probably better to do that as a decimal because I can't really put 47 degrees, 40 minutes in my calculator. So let's convert that. 40 minutes, well, there are 60 minutes per degree. So 40 divided by 60, that'll tell me how many degrees that is. So 40 divided by 60, that's 2/3. So 47.6 repeated. We're going to take, that's the angle. And that'll be the overall height of everything over this 50-foot adjacent, because that's your opposite, that's your adjacent. So 50 times the tangent of 47.6 repeated, and it is in degrees again, that's going to tell me the total height of everything. For that one, I got about 55 feet. I rounded up a little bit. It was about 54.9. I rounded up a little bit. So I think that's probably close enough. And then finally, if I want to find the height of just the steeple part, well, if the whole thing was 55 and that part was 30, or the building was 35, the rest would have to be 20. So final answer here, roughly 20 feet. And if they want a more precise answer, we can always include more decimals, but that's the idea. 31 is one I really like. I had to do this in real life before we had the internet to look up all the positions of where satellites are, put your coordinates in, all that. I had to actually do this for real to aim a satellite before, and it worked. So there's a couple things that you have to kind of assume here. One thing that I wish the book would have put this in there, because they show the orbit of the satellite kind of in a dotted line, but they don't include this right angle. Now, I know that's got to be true from physics, because if the satellite's going in this orbit, this line that's tangent to the orbit has to be perpendicular with the Earth. That's just how orbit works. So that should be a right angle right there, which means that this piece is also a right angle, and that's going to be really important when we get to the end. They did tell us this is a right angle. This line is tangent. So if you were standing on the Earth's surface and looking back at the satellite, that's tangent to that. And that's about all we do know. So what we can fill in here, we really want to get this angle, because we don't really have a way to get this angle yet. But it will be the complement to this one, because that's a 90-degree angle. Now I've got an opposite side, and if you think about it, you really do know the length of this side, because that's the radius of the Earth, and from the center of the Earth to this point is also 4,000. So this whole side right here is 16,500. So we'll go ahead and label that in. Now at that point, since this is a right angle, we've got enough to do a sine ratio, because that's an opposite and that's a hypotenuse. So sine of the angle would be 4,000 over 16,500. So this would be a place where we would do arc sine. If we do arc sine, we get about 14 degrees. And again, you can include more decimal places if you like. I'm just trying to get the idea across. So if this angle is 14 degrees and the whole thing is 90, and that's going to leave us 76 degrees for that angle right there. This problem's pretty open-ended. There's a lot of approaches you can take, so I'm just going to go through the most direct route that I know. Just kind of first glance here, we've got an airplane that's traveling this direction toward us at 550 miles per hour. And it's, we take a measurement at one point, and a minute later we take another measurement, so it's closer to being overhead at that point. If you think about that, we can figure out exactly how far it traveled in 1 minute. So that's kind of where I would start. I'll just do a little conversion table, 550 miles per hour, and we want to get that to feet, so 1 mile, 5,280 feet. And then we want to get hours to minutes because we want to know how far this thing's traveled in 1 minute. So 1 hour is 60 minutes. So 550 times 5280 divided by 60, and all the units have crossed except for feet per minute. So this thing has traveled 48,400 feet in that 1 minute span. So that's the distance from the first, if you think about just being plumb with the ground, and from here to 1 minute later. So this distance, if I can scoop this. So this distance from here to here is 48,400 feet. So we do know that definite as concrete. Now that's pretty much all we're given for sure, except for the angle measurements. And that's all we've got. We've got to find the altitude from all of that. So at this point I recommend filling in some variables. We're going to need A for altitude. And I'm going to use D for this distance right here because I don't really know what that is, but I kind of need to know how far the airplane is from me. Just looking at this triangle right here, I've got an angle, and I'm going to want to find the altitude. And it's going to be hard to find this distance, but since I know this piece, I'm pretty confident I can find this one eventually. So that's what I'm going to fill in. I'm going to put an A for altitude. That's the same thing here and here. It's assuming it keeps the same altitude. And then we'll put a D right here for distance. You can call these whatever you want, but I think that kind of makes sense. So now let's look at the two separate triangles that we have. Let's set up some trig ratios. So for 57, we have an opposite and an adjacent. So tangent of 57 is A over D. And in 16, pretty much the same idea. You've got opposite and adjacent. Just got to be careful how you set this up. So tangent of 16, let me make that more proper, put degrees and put it in parentheses, is the opposite, which is A, altitude, over the adjacent. And be careful because this big triangle right here, this whole side is your adjacent side. That's D plus the 48,400. We've got two variables and ultimately two solutions we got to find here, but we've got two equations. So we should be good to go. And just kind of looking at this, it looks like A would be pretty easy to solve for in both cases. So I'm going to go that route. I'm going to solve for A in both cases, and then we'll eventually set those two equal and see what happens. So A is the same thing as tangent of 57 times D. And A is also, I'm going to go ahead and distribute this out. Well, actually, I'll take it back. I'm going to hang on. I'll distribute it in a few minutes. So D plus 48,400 times tangent is 16. But since those are both equal to A, they're both going to be equal to each other. So distance times tangent 57 is going to be equal to, and now I'm going to multiply them out, D times tangent 16 plus 48,400 times tangent 16 also. So that tangent 16 distributes to both. At this stage, I've got D on both sides, but it's multiplied by a tangent in each case, so I'm going to start working toward getting those on the same side. So D tangent 57 minus D tangent 16. I'm subtracting that off of both sides. And at this point, I'm going to go ahead and multiply these two things together. That's going to give me 13,878 feet. And I'm just going to leave it at that. This is going to be close enough. Y'all can use more decimals and get it more precise, but that should be good enough. Now to get d by itself, I do need to factor here. So let's factor d out. Leaves me with tangent of 57 minus tangent of 16. And that equals 13,878. So now let's subtract those two things. Tangent of 57 minus tangent of 16. So I'm going to get 1.253d. And I'm going to use all the decimals in the calculator. I'm just going to write a few down here, but when I actually divide, I'm going to use all those. So d, when I do my division, 13,878 divided by this number, gives me about 11,074 feet. Now that's d, so this, we're ultimately trying to find the altitude. Let me go back to the diagram and talk about what we've got right now. So this distance from where I am now to where the airplane is a minute later from where I began, we know that's 11,000 and whatever odd feet. So at this point, there's different routes we can go, but I think I'm going to go right here. I've already got an equation defined. Really, I've got both, but this one's the simplest. It's defined for altitude. If I just take that distance times tangent of 57, we'll be good to go. So let's go ahead and do that. Altitude is going to be that distance times tangent of 57, and that should do it. So let's see what we come up with. We get 17,053 feet. Yeah, that will do it.